Okay, so thank you everyone to be here from this talk, so which I will introduce Eclipse Zenoh, and also the way it can help to expand MQTT systems that you may have. But at first, what is Zenoh? So Zenoh is a protocol that we designed and implemented all along, and which brings nice feature to communication middleware. So, of course, Zenoh supports the publish-subscribe paradigm that a lot of middleware also supports in push mode. So you can declare some peers that are publisher for some topic of data, and some subscribers that will receive those publications from the publisher. It also supports pull mode, in which the data is pushed until the library implementing your using by your subscriber. But your subscriber will decide when to pull the data, the latest publication, at its own pace. So it might be useful in some cases where your subscriber is not so powerful to handle a high throughput. It will just react on the latest publication. But Zenoh supports also storage mechanism. So in Zenoh, you will have the possibility to declare some storage, which subscribe to all the publications, to a set of publications, and all the publications will go to this storage to be stored in some backend technologies. And later on, you can have a peer that also perform a GET request to get a history of publications or the latest publications that have been made on one or several key expressions. So storage will possibly reply with one or several answers that have been, depending what is stored in the storage. So, but because we have get reply mechanism in Zenoh, you can also use it to implement on-demand queryable. So really queryable that you will implement yourself and reply with your own values that are possibly computed on demand to a request. So with this mechanism, you can also build a RPC, remote procedure call mechanism, with Zenoh. All of this in the same single middleware. So, but what topology supports Zenoh? A lot. It supports peer-to-peer mode communication in a click mode or in a mesh mode. In a mesh mode where not all peers are connected with each other, but it means that one peer of Zenoh, for instance, might be able to route the publication from one peer to another peer if they are not directly connected. We also support brokered mode. We developed in Eclipse Zenoh a software router that is named Zenoh router, and which is able to route the data from one client to another. So when a client is publishing the data, it's routed to other clients, similarly to what is done with the MQTT, for instance. But knowing that also a peer, because we, as I previously mentioned, a peer is also able to route, you can have client application connected to peers, and the peer will also route the data between client applications. So the difference between a peer and a client in Zenoh is that a client has embed less code because it doesn't do all the routing, it doesn't participate to the routing algorithm for Zenoh. While a peer may be able to hold some information about the routing table, so to be able to route data from a peer to a peer or from a client to another client. But the Zenoh router is not only a broker, it's also able to perform some intelligent routing. So you may have different routers that are connected together, and all the publication from one client will go through different hops of router to go to the client interest in the publication. And the same for the queries and replies. And all of this can be mixed together in a very big system, for instance, where you can deploy all your routers in different places in the network, in the edge, in your LAN, in the cloud, in various cloud providers. You can deploy everything everywhere you want and still have either client communication application communicating directly with a router, either in some subsystem, some peer-to-peer communication that will occur only locally, but when required, some publication will be able to go outside and possibly over the internet or up to the edge computation. So, Because we implement the protocol, we design it to work really on low level. So Zeno is able to run as low as a data link transport. By default, we support TCP, UDP, QUIC, WebSocket, but also thread, serial communication over just a serial port. We also made experiments with Bluetooth, with some profile of Bluetooth. So really, lots of communications that can be implemented from Zeno. We have an API that allows you to implement your own transport if required, or we can also implement it for you. Zeno is mainly built in Rust. So all the core of Zeno, including the router, is developed in Rust. We have bindings for other languages like Python, C, which are all based on the Rust API. In the future, we'll develop more APIs like C++, Java, Go, or other that may be required from users. For embedded and constrained devices like microcontrollers, we have a specific C version of Zeno, which is pure C, which is named Zeno Pico. So this, it doesn't have yet all the features that we have in Rust. For instance, with regard to routing protocol, it only acts as a client. It can also act as peer-to-peer, but only leveraging UDP multicast. So still, we are able to run Zeno on some such of devices, like an ESP32, for instance, with only 200 kilobytes of memory. Zeno is also extensible, meaning that the Zeno router has a plugin loading mechanism, plugin in form of shared libraries that needs to follow a certain interface. So we already implemented some plugins for REST, for instance, to provide a REST API to Zeno, where every HTTP put is translated into a publication on Zeno, and also leveraging HTML5 server sent event, which is a way a web server can push data to a consumer. So you can have in your web browser, for instance, a subscription using SSE that will be translated into a Zeno subscription. So the data will be published on the Zeno system, will be pushed up to your web browser. We also have a DDS plugin that we use because the ZettaScale company that is managing Zeno is also managing Cyclone DDS, which is an implementation of the DDS specification that is widely used in robotics, for instance. So we have a plugin for DDS that translates all publication subscription made in DDS into Zeno publication and subscription. So we made some nice demonstration with this in the context of ROS2. ROS2 is a robotic operating system where we show that we can bridge all the ROS2 communication with Zeno up to the internet, for instance. And for this talk, I will talk just after about the MQTT plugins that we have. We foresee also to have a Kafka plugin in the future. And with regard to all the storage implementation, so as I mentioned, Zeno can store data. It will store those data in various databases that we use for implementing that are also pluggable. So we have InfluxDB for time series data that can be stored. We have RocksDB for a file system key value store. We have file system also. You put your data, it will be stored ready in a file, or you can expose your existing file in Zeno that can be queried via GET. Or something as simple as a memory storage that will just store your values in a hash map in the memory of the Zeno router. So, few numbers with regard to Zeno. With regard to performances, that's a result we had recently. So these are made on this hardware, so quite high-end hardware, and with a 100 gigabyte Ethernet. So as you can see, for very small payload, we are up to 4 million messages per second. And with regard to the usage of in throughput, so there is a comparison here with iPerf. So iPerf gives you what you can get as most from your network, right? Because, well, you can't really have the 100 gigabit Ethernet that you're plugging, because there is a driver to take into account the hardware to connect to the Ethernet. So with a basis of of I think it's 60 gigabytes per second, Zeno can go up to little more than 50 gigabytes per second in payload as soon as you use 8 kilobyte payloads. Latency, we have a very low latency of 15 microseconds. And recently we had a very nice feedback on our Discord channel from a user, which is comparing Zeno latency with regard to gRPC for query replies, and he had very good results. So he likely replaced all these gRPC usage with Zeno. The good point in Zeno is also that we have a very little overhead with regard to your payload, which can go up down to 4 or 6 bytes depending the profile you're using. Some comparison with throughput. So for instance, here we made a comparison with Mosquito, and you can see that, well, Zeno has very, very good results that can be used then in the presentation after. I will show that it can be used really to have a federated MQTT. So the backbone, if Zeno is used as a backbone communication, there will be no problem to handle a lot of MQTT messages. On microcontroller, so with Zeno Pico, you have here some numbers of memory usage. So depending on the platform, you have already the OS, which brings some memory usage. You have the binary itself, so an empty binary with just a Zeno session that brings something, some extra overhead, and then here you have the overhead of just declaring at Zeno publisher. So now the MQTT bridge. So MQTT bridge is available on GitHub. You can have a look and compile it. So it comes in 2 flavors. Because it's implemented as a plugin, so it can be built as a dynamic library that will be loaded dynamically either at startup, either at runtime by the Zeno router. Or you can build it statically with a main function as a standalone executable. So you can deploy it as a single application on your host, and it can hack peer-to-peer with other Zeno bridge, MQTT, or other Zeno applications, which are also peers applications. And it's implemented as a MQTT broker, meaning that if you have an application, MQTT application, connecting using the locator of this bridge as a server, it will publish a temperature, for instance. There will be a callback in the MQTT bridge which is unpublished, and it will react and just publish back the same information, the same payload with the same topic name onto Zeno, where you may have, for instance, a Zeno subscriber receiving the data and displaying this data. On the other way, if you have a subscriber, the unsubscribe callback in the bridge will be triggered. It will create a Zeno subscriber corresponding to this key, subscribe key. And whenever a Zeno application publishes data on the same topic, it will be forwarded to the MQTT subscriber. With regard to subscription topic mapping, so MQTT, you know, supports some matching character like plus or sharp. In Zeno, we have similar concepts. It's just the symbol which differ. Star corresponds as any string without a slash, and star corresponds to any string, including a slash, like in a recursive path. Use cases. So one obvious use cases that we foresee is decentralized MQTT. In the Zeno Bridge MQTT, you have an option also to add a scope, which will be a prefix used in the Zeno republication added to the topic name of your MQTT. So, for instance, you may have various objects in your home that will publish all on the same topic, right? Because you all build the same objects. But still, you may prefix them with home1 or home2. And onto Zeno, it will be transmitted as home/1/your device topic name. So it can go up to an edge server, for instance, that will also have its own MQTT environment, where you may have some intelligence in this. So again, you will have some translation to MQTT. And you can also have an MQTT system in the cloud, where with, for instance, an InfluxDB database that will store everything or partial of publication. And so you may have in this way a totally decentralized MQTT with MQTT in various places in your system. So some other use case, integration with MCUs. So you can have with Zeno Pico some MCUs that are publishing or subscribing data to Zeno that are then translated to MQTT via the MQTT bridge. Cross-WAN bridging. So for instance, if you have two different MQTT systems, if you have two different MQTT systems behind two different NATs, you may deploy two different MQTT bridge in both of your LANs, interconnected either via Zeno router, and that will cross the NAT, because actually there will be only one single TCP connection going out, so no problem to cross the NAT here, and the Zeno router will route back this to the other router via the outgoing TCP connection. Of course, if you are able to configure your NAT with port forwarding or public IP, you may also have a direct connection with bypassing the NAT. Other use case is integrations. So you may have a lot of integrations using Zeno. So already you can do publication and subscription of your MQTT system via Zeno, via the REST and the SAC plugins. You can also have integration with DDS, so integration with Robotics that uses DDS. And in the future, for instance, integration with Kafka or whatever plugins we may want to implement in the future. So last week I was actually at the RocksCon conference for robotics, and we had a demonstration that I will explain here. So it was oriented to robotics. So we had a robot, which is a turtle bot used for studying robotics, and which runs Eclipse Cyclone DDS within ROS2 environment. It also has a camera on which we have a Zeno application that just captures the frames and republish the frames to Zeno, frame per frame, with encoded as JPEG. There was a router, Zeno router deployed in a Linode host, so just a VM, Ubuntu VM in the cloud. And this router has also the REST plugin and the web server plugin to forward, to connect to HTTP. So on my phone here, I get the feedback from the camera. I get all the picture from the camera, but also I can publish some commands to move the robot all along. And in addition of this, on the Raspberry Pi, we have the ZenoBridge MQTT with a ZigBee to MQTT application, and with a ZigBee button connected. So in this demo here, you can see the Raspberry Pi with the ZigBee key, the ZigBee button. So this ZigBee button is connected to the Raspberry Pi, and whenever I click to the button, the ZigBee will transmit the message to MQTT. The MQTT bridge will transmit it to the bridge to DDS, and it will be translated. There will be a little Zeno application that translates the payload, which is in JSON, into a twist message that is used using the DDS encoding. So there is just a little transformation of data, just a little script that in Python script that is tens of lines of code. And you can see that the robot is moving wherever I push the button. So, thank you. I think I was quite fast, so we have plenty time for questions. Do you have any questions? Yes?
So my question...
Hold on, I will give you the microphone for the recording. Thank you.
So in that demo that you have over there, what's the typical latency that you would get, for instance, from pressing that button until the robot gets its message?
So the latency we have actually, well, we didn't measure, but the most latency is just the time for the ZigBee communication to occur up to the ZigBee to MQTT tool, because you know, in the button you have two modes. You can have one single click, one double click, or one long click. And just the time that the button reacts to is it a one click or a two click, that's already the delay you have. And then you have already the delay of the Wi-Fi, which is already, well, few milliseconds.
Thanks.
Yes, if you can pass the microphone.
Great project. Thank you for the presentation. Does Zeno have a recommended way or embedded way of handling payloads in MQTT messages, or like Sparkplug, or yeah?
So no, Zeno actually accepts just byte buffer as a payload. But with this byte buffer, in addition, you can provide a MIME encoding specifying which way your payload is encoded, so we can support anything. Knowing that the MIME encoding, you as a user specific as a string, but we have a set of very known MIME encodings that we on the wire transmit just as a single integer, again for bandwidth efficiency. So you can perfectly use JSON, DDS, whatever you want. Sparkplug might be a good idea also to add some plugins or something to support Sparkplug. Yeah. So thank you for your, other question? Yeah, sure.
Just a small question. So based off the graph, is there some elasticity also when it comes to the Zeno? This was not the bridge, the router.
Mm-hmm.
Because if we get, I don't know, we have 50 million devices out there, right? Say maybe a certain amount of message, so I need maybe to be able to duplicate. Is there some elasticity there?
Well, so we plan to have some elasticity. The only elasticity that we support right now is per connection load balancing. So you can have a bunch of routers, for instance, deployed in your cloud or wherever, and you can use a DNS load balancer that will balance all your client connectivity to the different routers. That's the very first elasticity that we can provide. Later on, we foresee to have more fine-grained load balancing, possibly per message or per publication, with probably some pluggable load balancing strategy that will get some information about what's the most used CPU or bandwidth or whatever information you get from your infrastructure. Okay, so thank you for your attention, and if you have more questions, come to us and come to our Discord channel. And also this afternoon we have Julien Loudet and Gabriele Baldoni that are giving a talk at 3:15 about Zeno Flow, which is an extra layer above Zeno for data flow programming. So that might be also very interesting for various projects, including robotics and software and autonomous vehicle. Thank you.